Okay, yeah. So so apologies about last week. So you did linear regression last week, and I hope you all got on okay with the Kaggle page. So I know you were using RStudio in PM272. So a lot of people, when they develop stuff online in a collaborative way, especially if they're doing machine learning, they will use things like Kaggle and Google Colab, which is another version. And it's basically like this notebook style of things that we're working off. And we'll go through a notebook for logistic regression today as well. So I hope you all got on okay with that. We definitely need to be leveraging the free GPU that we get from Kaggle when we do some deep learning towards the end of this course. Okay, so yeah, today is about logistic regression. If linear regression, let me just get my pointer, there we go. So linear regression, we were looking at this kind of problem. We had a continuous variable on the x-axis, and then we had a continuous variable on the y-axis. And there's a few different things we could do. We could essentially use this line of best fit, which we went over how to optimize that in last lecture. We can use this line of best fit to say, well, given a value of x, we can predict the value of y. And also if we have multiple continuous variables, i.e. multiple linear regression, we can take multiple variables and still predict the value of y. And linear regression is useful because it can tell you which variables contribute most to that prediction of your continuous variable y. So it's a very useful thing. But today we're going to look at logistic regression. So here we have a continuous variable on the x-axis. Okay, but we have a binary variable on the y-axis. So you can see that we've got 8 data points, 4 of them on the left are split and they take the value of 0. Their continuous variable, and the y variable would be 0. And on the right-hand side, the y variable value would be 1. So this is slightly different because we're not looking at continuous versus continuous. And this is useful though, because for example, if we wanted to work out the probability, i.e. yes, no, of developing lung cancer, and the variable that we had, continuous variable that we had, was the number of cigarettes someone smoked per day. Logistic regression is ideal for this kind of problem, where we want to not only say, yes, they will develop lung cancer, but have a probability associated to this. And so if you cast your mind back to PM272, we looked at decision trees, which is a machine learning technique. And so this is a classification. So even though it says regression in the name, there's going to be a sleight of hand where even though we are plotting a line of best fit, if you like, it's going to be turned into a classification problem like we did with decision trees. So you can get the label and the probability associated with that. So, just a few thoughts on why a linear regression wouldn't be good for this type of problem. In life, things aren't this simple. If you look at risk of developing lung cancer against number of cigarettes smoked per day, if we plotted linear regression, what it says is that for each additional cigarette you smoke per day, you linearly increase your risk of developing lung cancer. But we know this isn't true, which is why the GP asks you things like, do you smoke 5 or 10 a day? They never ask, do you smoke 7 or 8 a day? Because it doesn't really matter, okay? So we kind of have this inference that linear regression, plotting just a straight line here, wouldn't be a good way to map the number of cigarettes smoked per day to the probability of experiencing an event such as lung cancer. So the question is then, what function can we use, or rather, what function is the logistic regression going to use? We know it can't be linear. It must have probabilities built in, be able to handle this, i.e. you take an x variable and it must map to a y variable between 0 and 1. Okay, so if x-axis, it can be any number you like, 10, 100, 1,000. The y variable, it must be scaled between 0 and 1, i.e. we're working with probabilities. Okay, and as the name suggests, logistic regression is a regression technique. So we are going to plot a line, but it's not going to be a straight line. It's going to be a nice curvy line, which builds in the complexities of, not just smoking one more cigarette linearly increases your risk of developing lung cancer. So basically a primer on logistic regression to get behind some of the ideas and how we're going to map a continuous variable to a probability. We need to talk about how logistic regression outputs an analysis plan. So if any of you have ever come across logistic regression before, if you've done a stats module, maybe with Mike Gravener, it doesn't really matter. If you have, and you've done logistic regression, you might know that logistic regression, it can output its results in two ways, and that's either in odds or probabilities. We're interested in probabilities for this, okay? If you're a statistician and you're not doing machine learning, you're not classifying something, you're probably more interested in odds. But we're going to go through both today and see how odds and probabilities are related. So if you ever come across logistic regression in the wild, you'll be able to spot it. And if it's expressed in odds, you can just turn that into a classification problem really easy, okay, by converting it to probabilities. So yes, results of logistic regression can be reported in two ways, and it may be a bit confusing, so we're going to clear all this up. When we report things in terms of probabilities, this is a classification task. What's the probability you will develop lung cancer or so on? An odds ratio are reported usually when you've done a regression analysis. So I appreciate this is all sounding pretty confusing. We're going to demystify this whole thing. Logistic regression is a regression. It's just got it's like a two-bladed sword, if you like, two-edged sword. So this means that sometimes you might read studies that have used logistic regression and see something like this. A study found developing lung cancer in smokers has an odds ratio of 2. So i.e. people that smoke are twice as likely to develop lung cancer as people who don't smoke. And you can scale this up. So, if you smoke 50 a day, you might be 4 times as likely, and so on. And so I think we're kind of used to seeing these sorts of sentences in newspaper headlines, right? People who do this, eat an apple a day, are less likely to develop whatever, okay? So this is basically, we're working with odds, okay? So statisticians in stats land, this is typically what you're using logistic regression for, to produce a sentence like this. However, we're doing machine learning. So what we would like to do is say things like the algorithm was able to predict lung cancer in patients to 87% accuracy. So you know that if a patient walks through the door, you take a load of data on them, and you want to predict if they're going to develop lung cancer, you know that algorithm is 87% accurate. So if it pops out and says, yes, you're going to develop lung cancer in the next 5 years, and they say, how certain are you, doctor? You can say 87% certain. Okay, so it's just a slightly different way of doing things. And all through this course, actually, when we're doing supervised classification, we're dealing with probabilities mainly. But they're not the same. Odds do not equal probabilities, but they are linked. And there's a nice equation to do this, which we'll go through now. So we'll talk about odds for a second. If you were interested in the odds of Liverpool winning a match, and it says something like 4-1, so I'm very sorry to any Liverpool fans, you can't win them all. So the odds of Liverpool winning, if it's 4-1, that means for every 5 games, they will win 4 and lose 1, okay? However, the probability of Liverpool winning is basically the number of times they win over all possible outcomes, win or lose, okay? So in odds, it's the odds of winning over the odds of losing, essentially. In probability, it's how often you'll win divided by all possible outcomes. So we see that is 80% in this case. So odds are the ratio of one outcome over the other outcome, winning over losing. Probability is the ratio of one outcome over all other outcomes. So there's a slight difference, but it does make all the difference in logistic regression. Odds and probabilities, though, can be related. So if we consider this following example, if the odds of winning was 5-1, or I equals 5, then that means the probability of winning is 5/6. Okay. We can also say that the probability of losing is 1/6. So to complete the fraction, we got 5/6 plus 1/6 equals 1. We've arrived at our probability equals 1. So we can write this in a certain way. And this also means that the probability of losing then is 1 minus the probability of winning. So 6 over 6 minus 5 over 6 equals 1 over 6, okay? So if we take the probability of winning equals P, then the probability of losing is 1 minus P. So probability of losing is 1 minus the probability of winning. So the probability of winning divided by the probability of losing equals P divided by 1 minus P. We work those fractions out, just plug in the maths. 5 over 6 divided by 1 over 6. So you flip one of those fractions and multiply them. And you end up with 30 over 6 equals 5, i.e., we go back, odds of winning equals 5 over 1, okay? So that means that the probability of an outcome can be related to the odds of an outcome by P over 1 minus P. The probability of winning divided by 1 minus the probability of winning, i.e. losing, equals the odds. So this means that when you see a sentence in a paper, such as they are twice as likely to develop lung cancer, you can convert that back to a probability. You can just switch them over using this simple formula, okay? So if you read something like that, you can say, oh, okay, well, if they're 2 times likely to develop cancer, what's the probability that they'll develop cancer? And you could easily plug these in. So this means no matter how the results of logistic regression are reported, we can interpret the results as odds or probabilities. So we know that odds aren't the same as probabilities, but we can relate them. So this is good. So we've got our two-edged sword here set up. So we just need to discuss one more thing. So odds, they kind of have this undesirable property. So if you look at 1 over 10, how these scale up, how these odds scale up. Odds between 0 and 1, they shift very little each time. So 0.1, 0.25, 0.33, a very small change. However, as soon as you reach an odds over 1, like 4 over 1, 2 over 1, and so on, these start to balloon. So actually, it kind of is a bit misleading to say if you just go from 3 to 1 to 4 to 1, it's going to be the same change as if you move from any other odd f one other odd. So this is kind of misleading and it's undesirable. But if you take the log, so this is where logistic regression comes in, the name gets it from. If you take the log of the odds, it's completely linear. So wherever you are, so if you take log of 1 over 10 against the log of 10, it's just minus each other, okay? So this is much easier to work with. Things don't balloon quite so much, and this is where logistic regression gets its name from. Okay, so last week when you did linear regression, you solved an equation which was y equals mx plus c. Okay, so y is the continuous variable that you want to predict. X is the continuous variable that you have to make that prediction. And when you optimize to arrive at a line of best fit, you have m equals the gradient, the slope, okay, plus c. And you shift that line across the x-axis. So you have a y-axis intercept. In logistic regression, instead of, remember, we're not trying to just predict a continuous variable, we're trying to predict a binary variable. So we can just plug in the log odds. We substitute the log of the odds in for y. And suddenly, this problem now becomes a logistic regression equation rather than a linear regression equation. So yeah, here, log of the odds is just simply y if you were doing linear regression. So this is good. So we can relate the log odds of something happening, in our case winning a match, to a variable via a regression equation. Okay, so regression is always takes the form of something equals a slope multiplied by the variable of interest plus an intercept. That's what regression is. And so for example, if we add the percentage possession of the ball, so if a team has 80% of the ball, maybe they're Barcelona or someone like that, then you might associate a higher probability of winning simply because they have more possession. And so you can plug those kinds of things into logistic regression, and you can get the probability that Barcelona would win, or you can get the odds that Barcelona would win. So, when Betfred and Paddy Power or whatever are updating their odds live, basically they're using logistic regression in the background to compute these odds. So you can lose all your money. We did multiple linear regression as well. So you can just add in more variables. You can have X, Z, and whatever. So perhaps you're interested in both the percentage of possession the team has and the total number of the sum of the transfer fees in the squad. So Manchester City famously have a very expensive squad. You might assume that squads which cost a lot, they tend to do better than squads that don't. Okay, so that's the wisdom here. Let's go back to health. Okay, so in our lung cancer example, we wanted probability, not odds, or even log of odds. So at the moment, we're doing regression. Okay, we're plugging in all our variables, and we're getting out as an answer the log of the odds. Okay, we don't want the log of the odds. We're not doing traditional statistics. We want the probability. So all we need to do is rearrange the p. So we have this example. We want the probability, not the log of the odds. So we're just going to rearrange this equation for p. Okay. So this is our regression equation. The log odds equals mx plus c. So if you remember your GCSE maths, if you take the exponent of a log, then you just move, then you take the other side up. So if you exponentiate both sides, we remove the log, and obviously we exponentiate mx plus c. And then we can move the 1 minus p over to this side by multiplying both sides by 1 minus p. So we need to get this p over to the left-hand side, okay? So we can expand this. So we have 1 times e to the mx plus c minus p times e to the mx plus c. Okay, so we've expanded this out. Then we can take over this term on the right to the left-hand side. So we're getting there now. So if we add this to both sides, we get this. And then we can factorize this as well. So again, you know, a bit of GCSE maths coming in. If you can factorize this to express it in this way. Basically, we've just collected the p's on the outside of the bracket, right? So if you multiply those out, we get p plus p e mx plus c. And then we just need to move everything in this bracket over to the right-hand side. So we've done a bit of magic. We've rearranged for p. So we have this horrible looking equation. It looked okay up here because we're familiar with linear regression. Something equals mx plus c, and now it looks pretty horrible, right? But anyway, this is what's known as the sigmoid function. Okay, so if you imagine this is our y-axis, and we want to express this in terms of a probability, i.e. a value between 0 and 1, and we want a nice complex non-linear function, this is exactly what the sigmoid function is. Okay, so we get slow growth here. So if you smoke 1 cigarette, 2 cigarettes, 3, even up to 5 cigarettes, it's really not going to increase your risk that much. Don't quote me, I'm not a doctor. Not that kind of doctor anyway. Okay, but when you start ramping up to 10, 15 cigarettes, then your risk ramps up really quick. Okay, and then it doesn't make too much difference to your risk if you smoke 90 or 100. I don't know who smokes 90 or 100 cigarettes. So this is an ideal function because we can put in a continuous variable. I know this doesn't map to number of cigarettes because you can't get -6 cigarettes, but it's just an example. But anyway, you can put in a continuous variable, x, and it maps to y between a value of 0 and 1, i.e. probability, and it encapsulates a lot of the complexities which you don't get in linear regression. So this is called a sigmoid curve. When we look at artificial neural networks later in the course, we're going to be using this sigmoid curve again. Okay, so logistic regression is used at quite a lot of places in machine learning. Okay, so just remind ourselves, in linear regression, m was the gradient or the slope. Okay, so you can have a steep slope, you can have a shallow slope. You're just basically sort of rotating this line in the middle. Okay, we're just adjusting the slope. And c was the y-axis intercept, i.e. you can shift this straight line left or right, and it will intercept the y-axis in a certain place depending on what the value of C is. So how do these variables translate in logistic regression? Okay, so if we look at M first. So if you have M equals 1, you have this black sigmoid line here. And if you keep increasing the value of M, you can see you kind of squash the curve to the center, right? So it's quite spread out when M equals 1. And as you keep increasing M, it squashes and it almost looks like a step function, okay? So, you know, if the value is anything below this value here, then it's just 1. And then there's a very narrow but fast growth in the middle for M equals 4 and so on. So this is how M looks like. Remember, in linear regression, you just tilt or rotate the line. But in logistic regression, we're squashing this sigmoid function with M. And C is pretty much the same, actually. It's the same behavior as in linear regression. You just shift the curve left and right. So C equals 1, it starts in the middle. And as you increase C, you just shift this curve to the left, okay? And it does make a difference because if you have a value of, say, 50, we can look up and we can see that our risk of something, whatever it might be, is just below 0.2, 20%, okay? So we just take this up here and go across. It's just below 0.2. But if you've optimized this curve and C happens to be equal 4, well, if that same value of 50 now maps to 40% risk, okay? So now we know the curve that we're going to be using, or the function, this is a sigmoid function. We know how M behaves and we know how C behaves. What do we need to do? We need to optimize M and C. We need to find the best value that fits our distribution correctly. So, you know, in linear regression, we did the same thing. We optimized M and C, and we used partial linear least squares to do that. We just measured the residuals between all the points on both the x and the y-axis and took the average, and we came up with our value called R squared. Okay, so how do we do this for logistic regression? How do we optimize for M and C in logistic regression? And remember, throughout this course, you will hear me say the word optimization so many times you could set up a drinking game and be pretty blotto by the end of it, okay? So optimization is the theme of this course. So how do we optimize them? We can't use linear least squares in this case because we don't have a distance in the y direction, i.e. no residuals. So what can we do? Well, we can use a method called maximum likelihood estimation. It's used all over the place. It's a general purpose. Basically, any distribution you want to optimize a function to, you can use this method called maximum likelihood estimation. So let's have a look kind of what goes on in MLE. So, you know, if we have a problem, we can say things of MLE such as, I expect to see the majority of these data points covered in this function when I use a certain distribution, i.e. values of M and C, okay? So it works for any distribution, and I'll just to prove this, I'll go through the normal distribution. So if we have some data points, just 1D, one-dimensional, we have our normal distribution, or Gaussian distribution, it's sometimes called. You know, if you've ever done a student's t-test, you're looking at normal distributions. You know, how well does this distribution fit our data points? So if our mean is here, and our standard deviation is here, well, these red points, they're really not covered that well by this distribution, okay? We're expecting most of our data points to be under this bell curve, and actually that we expect them to cluster around the mean, okay? But in this case, what we can see is that if we had put in values for the mean and the standard deviation, optimizing those two, we wouldn't have a very good distribution here. So the maximum likelihood distribution is failed. However, if we have this kind of distribution, now we can see that most of the data points are under this curve. They fit under there quite nicely, and actually they all cluster around the mean. So basically what we've done is we've just come up with the right values for the mean and the mean and the right values for the standard deviation. We've optimized on those two variables to arrive at a good distribution, okay? So we want to take this sort of way of thinking and apply it to logistic regression. So this is our distribution. Okay, we've got two distributions there. So we've got m equals 1 and c equals 1, and we've also got m equals 10 and c equals 2. This is what they look like. And so we want to see, well, which one best fits our distribution. So I think this is where, you know, we need the concept of training data to come in, because if we have risk of smoking, this red distribution here is just linear, pretty much everywhere where there's a data point, right? It's linear. But we know this isn't good because it's not going to give us nice complex values. You know, that model what happens in life, okay? However, this black sigmoid function where m equals 1, c equals 1, this is going to give us our nice, you know, how risk ramps up slowly, but then quite fast, and then so on. So we can just find the right distribution by saying, okay, well, which of these two functions, parameters, best models our data? So we use exactly how we did. We just find the best fitting distribution that fits our data in logistic regression. Okay, and any function that you have, no matter what it is, it could be weird and wonderful, you can always optimize that function using maximum likelihood estimation. So even linear regression, although I'm not going to show you how, we optimize linear regression with partial least linear squares. However, you can optimize it with MLE as well, because it's just a distribution, it's that F distribution, okay? So you can just optimize that. Okay, so, you know, that's basically logistic regression in a nutshell. What goes on? So we, instead of having a linear regression, we now have this nice curvy sigmoid function, which takes a continuous variable on the x-axis and it maps it to a variable between a value of 0 and 1. Okay, so this is ideal for probabilities. So let's look at how you use it in practice. So, you know, if this is our data, this is an example of really nice data. This is a perfect classifier, and we'll see why. So if, you know, this data point here has a probability of 25% of developing lung cancer, and up here is 75%, you'll notice that there are no data points. There's no crossover at all. So we have this region here where really you don't have to do much optimization at all, because most distributions, no matter what the value of M and X are, they will get 100% accuracy, right? However, in real life, data looks like this. So you'll have people which are very unlucky. They don't smoke much at all. The model says they have a 27% probability of developing lung cancer. However, they do go and develop lung cancer. Okay, this is real life. It's not as simple as how much do you smoke, this is your risk. So yeah, just to be wary, this is, you know, kind of what horrible real world data looks like. Okay, and therefore there's no perfect classification boundary for our algorithm. So how can we assess the accuracy of our model? So remember, back in PM272, we had looked at decision trees. We split our data into a training set and a test set. So we use some data here, usually 75% of your data, to train your classifier. Or in this case, when we say training for logistic regression, we mean we're going to optimize M and C with our training data. We use maximum likelihood estimation. We're going to optimize M and C. And then we have a test set, so maybe 25% or a third of your data. We're going to use this to predict, use our model where we know the value of M and C. We're going to predict what actually happens and compare it to what the prediction is. So if our model predicts this person here isn't going to develop lung cancer, but they do, then our model's wrong, and we can top this up and assess our accuracy that way. So yeah, just in summary, we use some training data to optimize the logistic regression equation, i.e. we might arrive at values such as this. So our value for M after maximum likelihood estimation took the value of 0.12, and the value of C took this. So if a new person walks through the door, you ask them data about X variable, Z variable, and so on, you can then predict the risk of something happening. You just simply plug in the data. So for example, in this case, if X equals 30 cigarettes, we just plug the value in for X, and out pops our probability of this, okay? So almost 40% risk. And if we can do this with just one person at a time. However, to really assess if our model has worked well, if it's accurate, you can go send it out in hospitals, clinicians can use it without worrying about it. You want to test your algorithm on lots of people, okay? And look at the statistics overall. How accurate was it on 200, 500 people, okay? So when we do this, we'll get 4 different types of results, okay? So if your model predicts the correct thing, so if they predict you're going to develop lung cancer and they actually do develop lung cancer, this is a true positive. False positive would be the model predicts lung cancer, but they don't go on to develop lung cancer. A true negative is that the model predicts no lung cancer and the person doesn't develop lung cancer, so that's correct as well. We've predicted that. And a false negative is that the model predicts no lung cancer, but the person does develop lung cancer. So this is probably the most dangerous situation in this case, a false negative. A false positive, if your model predicts they will develop lung cancer and they don't, okay, maybe they, I don't know. I'm not a doctor, I'm just trying to make this up. However, if you miss a diagnosis, a false negative, this is disastrous. So not all errors are equal, okay? Some errors are worse than others. In this case, if you miss a disease, i.e. false negative, it is terrible for the patient, okay? Do you remember confusion matrices from last year? Just about. Yeah. So, when you did decision trees, there was an assignment that you did, you had to work out and present the confusion matrix. So top tip, some students didn't do this in PM272. If you're presenting your results, I want to see a confusion matrix. I want to see the values in it, because if you say the accuracy is this by totting them all up, the only way I can check that you've done that calculation correctly is if I know all the values in here. So I know the number of true positives you had, the number of true negatives, and so on. So top tip, always present the confusion matrix. And there you go. So this equation for accuracy, if you might remember, is the number of true positives plus true negatives divided by all outcomes. Okay, that's your accuracy. We'll go over sensitivity and specificity in another lecture. And also another top tip, so thinking about your assignment when you get it, you never ever report accuracy on the training data. So this is because when you train a model, the model has access not only to the variables that you're putting in the model, it also has access to the true outcome or the ground truth, okay? So the model knows when it's training if they've developed cancer, yes or no. So if you report accuracy on that, it's completely biased because it had that available. It's like cheating in a way. So if I ever see you reporting accuracy on training data, you're going to get a lot of marks deducted. So that's another top tip. This is why we always do it on a test set instead. So the ground truth labels are hidden during prediction or in the test set. So it doesn't have access to what actually happened. It's going to make a prediction, and then afterwards we can go and compare. And that's the way to report accuracy. Use it on a test set. Okay. So in summary, I think what we'll do, we'll just wrap these slides up. We'll have maybe a 5-minute comfort break, and then we'll go into some code. So in summary, logistic regression is used to predict the log odds. So you'll get a result in log odds. By the way, when they say in a paper that the people are twice as likely to develop something if they do this compared to other people, what they've done is they actually got the answer in terms of log odds, and then to get the odds back, they just exponentiate that value. Okay, so they get the answer in log odds, they take the exponent of that log odd, and that's where you're twice as likely, 2 times pops out. Okay. Okay, logistic regression can also be used to predict probabilities. This is mainly what we're interested in on this course, okay, which can be used for classification purposes. Like linear regression, we are optimizing coefficients in an equation, and actually, like any machine learning algorithm, we're just optimizing parameters. Even though regression is in the name and it does fit a line, we saw it is a sigmoid function, it is a line, it's not a straight line. Even though regression is in the name and it does fit a line, logistic regression is used for classification. And it's just this unique property of a sigmoid function where it takes a continuous variable on the x-axis and it maps it to a value between 0 and 1 on the y-axis. So just that tiny fact turns everything on its head. It's not a regression in the sense of continuous variables against continuous variables. It's actually a classification problem using a regression technique, just for that sleight of hand. Continuous variable mapping to a value between 0 and 1. So what we'll see, has anyone heard of artificial neural networks before? Yeah, maybe in a sci-fi film or something, I don't know, Matrix and things like that. They're famous, basically, artificial neural networks. Actually, all artificial neural networks they're just sequences of logistic regression equations in a row. There's just loads of them. So, when everyone says, oh, artificial neural networks, they're complicated, actually, now, even though we've not taught artificial neural networks, if it's just a sequence of logistic regression progressors, nodes, if you like, then you kind of know how they already work. You just combine the results of multiple logistic regressions, and then you kind of vote which one's the best. It's a bit like, decision trees and so on. So, although we will tackle those on about week 8. Okay, so, logistic regression. Again, I always try to stress this point, because you'll probably see when you go for all your jobs, if you're going to do data science in life and so on, if that's what you want to do, I'll guarantee you will come across people which will say, oh, statisticians and machine learning people, they just don't like each other. They think each other are doing the wrong thing and so on. Logistic regression is the same equation. If you express it in log odds, that's typically what a statistician might use. If you express it in terms of probability, that's what people machine learning use. It's the same equation. We're working off the same things. And again, machine learning is just applied statistics at the end of the day. So if you hear people saying that statisticians are this and machine learning people are that, then they're wrong. Okay, so we'll have maybe a 5-minute comfort break, and we'll come back. And then what I'd like you to do is on the Kaggle page on week 2, there's a logistic regression notebook, which has just got one cell in it, which I'll show you what that looks like now. Okay, yeah, so if you open up this notebook, you'll get something like this. And we're going to be working with some diabetes data today. So we'll work on this thing. So I'll see you in about 5 minutes time. Okay. So I think we'll make a start then on this notebook. So, the coding is quite light today as it was in the last notebook. The code will ramp up a bit as we go through the course. So yeah, logistic regression. So if you're on the Kaggle page, so again, if you can just open up this notebook, and you should see in the top right somewhere, usually around here, which says copy and edit. And when you do that, you can get an editor where you can mess about with the script, you can edit it and so on. So we're using some diabetes data today. We can see what this looks like if we want, just by clicking on it on the CSV file. So yeah, there's lots of different variables, and what we're interested in is predicting the risk of diabetes, developing diabetes, or in this case, it could be classification. Do they currently have diabetes based on these variables? So you'll note that the value for diabetes takes on 1 or 0. So it's 1 if they do develop diabetes, or they have diabetes, and 0 if they don't. So we're going to read in this table. I've already just set us going. There was a few issues with separators in the CSV file, so I've just sorted all that out. We don't need to go through it. So if we run this piece of code, and maybe we'll output it as well, we'll say head of df, so the first 6 rows, and run this. Okay, so we get something like this. So this is just simply the first 6 rows of the data, and we can do other stuff. So we're going to explore the data set. So again, just getting used to notebooks. So you can have code cells. So this is a code cell, right? You can have a markdown cell, which is basically, you know, just writing and so on. So you can put something in here. You know, one hashtag means a header, like, you know, bold header, and they get smaller and smaller. So if we just try one and say, we're going to explore the data set. And then we'll click off it. So it looks a bit like this. And now we can create a new code cell. So add a new code cell. Right, so there's a few things we can do. So I usually start off with a summary df and see what that looks like. So we can get some simple stats. So for example, this needs to be a factor, if you remember factors. We'll do that in a minute. But you can just about see that the mean for this diabetes variable is 0.34. So the majority of these people don't have diabetes. Okay. We'd like this to be a percentage sign. If it was a factor, we could do this, and so on. So that's the first thing I tend to do, which is explore the data set. We can do other things as well. We can do a cross table. So we have a function called xtabs, which is really handy. So we're going to say that we're going to cross the diabetes column with the age column and say that the data equals df. Okay. So this is quite handy because you can see so each person, sorry, not each person, you can see a cross tab of ages versus diabetes. You can put in any variables you like in here. Lots of people have their own different ways of summarizing data. Another thing that you could do is, so actually we create a markdown cell. What are the data types? So we have this really nice function called str. You put in our table name, df, and it tells you for each variable what the data type is. So this can also be handy as well, especially if you consider that usually most machine learning algorithms, if you remember in decision trees, it needs a factor for the predictor variable. Okay. So that's just a bit of exploration. Again, you know, I encourage you to read around outside of the code that we do in these notebooks, because there's plenty of other ways to do this. You'll all develop your favorite way. Okay, so we need to turn this variable diabetes into a factor, because machine learning algorithms, they need the predictor variable to be a factor. A factor is basically not numeric, it's just like a categorical variable. So you can read factor as a categorical variable, i.e. yes or no. So we can do this. So let's just create a new cell, a markdown cell, and just say turn diabetes column into a factor. And by the way, if you don't want to use markup like this, you could always put a comment in like what the data types. This can work a bit better if you want to paste your code into RStudio, or you want to share your code for someone to run in RStudio. This is slightly better because when you paste this entire cell, they get the comments, whereas they don't get the comments if you use Markdown. It's completely up to you. I don't mind. Okay, so turn the diabetes column into a factor. So how do we do this? So we say we can access certain columns with this $ symbol. Okay, so df, and we're accessing diabetes. So we'll just see what that looks like. Just that is one column. So we want to turn this into a factor. We know from the str function that it's an integer. So we're going to say this column, we're going to overwrite it as a factor. So we say as dot factor df diabet. Okay, so that has run. And we can now just confirm that it is a factor by rerunning the str command, factor. Okay. So I'll just let you all catch up. I appreciate when you're online, you're looking at my screen and you've got to keep switching to your own screen. So I'll just leave a bit of time for you to catch up. But yeah, no. Yeah, also for everyone online, I'm kind of juggling a lot of different windows. So if you have a question, just shout it out. It'll come up on my laptop. It's very difficult to switch between the chat and hosting screens. So yeah, if you have a question, just shout it out. We doing good? Okay. So yeah, it might not look like much that this is a factor because the values are still the same, well, kind of the same. It does a little jiggery pokery, but yeah, it might not matter too much to you when you look at this because they're just still numbers at the end of the day. You might think that casting it as a factor would turn it into, you know, a string like yes or no. And we could do that. We could overwrite those. I'm not too worried about it today, but it does make a difference. So remember, you know, when functions take in some data, the first thing they look at is what is the data type of the thing I'm trying to read in. So for example, in a lot of machine learning techniques, if the predictor variable is a continuous value, i.e. an integer, it will automatically do regression, linear regression, okay? So all these algorithms we're going to talk about this term, they can do classification and regression. And then if you wanted it to do classification, then you have to turn it into a factor. So that's why that's useful. Okay, so let's move on. So we're going to actually run the model now. So I'll create a new thing here. So run the model, and we're doing logistic regression. So it's really easy. There's no packages you need to load into R. The logistic regression uses a library called stats, just the stats library, and there's a function called GLM, which does everything for us. So let's start off by writing this. So we say GLM, this is our function. I'm going to put in our data, diabetes column, and we're just going to read in 2 columns of data to make our prediction. So I'm just going to use BMI and age because I think they are related. Just that's my hypothesis. Data equals DF. And the way we say, so this GLM function can use lots of different statistical techniques. So the way we say to use logistic regression is we say family equals binomial. So you might hear people, again, usually statisticians, if they do logistic regression, you might hear it called binomial regression. It just means logistic regression. It's the same thing. You know, and as you might be aware, R it started out as a statistical software, open source statistical software, written by statisticians. This is a base package that has been in R since the 90s. So, you know, this is where it gets its binomial name from. So we can run this. Okay. So we've got a few things. For each variable, we've got our intercepts, our M values, gradients. So this is how much it squashes the curve for both age and BMI. And then we have our shared C plus C. So this is MX plus KZ plus C. That's our equation. Okay. So we can run that. We built a model. We should store this in an object. So we're going to store this in an object called, let's call it Logistic. Okay. And again, this summary command, you can apply it to lots of different objects in R, and it'll spit out something for you. So if we run this, we get a bit more information. So yeah, I'm not going to go over p-value. We went over p-values in linear regression. You can calculate p-values for logistic regression as well. So you get a bit more information in here. So we've got all I want to bring your attention to is the estimates, the intercepts, and the M values. Okay. So we built a model. So next, in a minute, to let you catch up, we are going to use it to make a prediction. Okay, so we're going to read in someone's data, their BMI and age, and we're going to get a probability out. Down a bit, or up a bit. Yep. There you go. Okay, so we've built our model. We've stored it in an object called Logistic, and we can apply functions such as the summary command to this object. So now we're going to use it to make a prediction. So the scenario is going to be, you're a clinician, someone walks through the door, you take down their BMI and their age, and you're going to put this into the model. So let's kind of simulate this, if we like. So we need an object to store the BMI and the age, if whoever this is. And oh yeah, it's me, BMI 25, age 33. Okay, so let's see what my risk is. So xval, we're going to store this object. You can call this object whatever you like, it doesn't really matter. It's going to be a data frame with just one row of data and two columns. BMI equals 25, and age, actually, yeah, so there you go, age equals 33. So we can store this. And if you remember from decision trees, I know it's probably unfair to expect you to remember all this stuff, but it will come flooding back. We're going to use the predict function, and it just takes two arguments, our model and our new data. So we say predict logistic and then xval. And we can run this. So this is odds. So we need to take the exponent of this. Just let you all catch up a minute. Just sorting out a problem in the class. So I think we can directly take the exponent here. And there you go. So remember, this is a log probability that we get, or sorry, log probability that we get out. So we just need to take the exponent of this to get our, real life probability, okay? So, for someone whose BMI, we've trained on some real data, by the way. This diabetes data set is real data. And so using our trained model, if your BMI, like mine was 25 and you're 33 years old, this would be your risk of developing diabetes, okay? Or this is, if I presented with these, what's the chance I have diabetes right now without conducting like a serum test or anything? The merits of this model are to be debated. Is it really that good if you only use BMI and age and so on? Obviously there's something to talk about there, but this would be your risk, 23%. Okay. So obviously you can play about putting your own things in if you want to, if you're not easily scared. Yes, question at the back.
Would that be the probability of the odds?
Probability. Yeah, I can go up a bit.
So the first answer you've got for the experiment is about that the odds.
Okay, so that's a simple prediction. You can add more features if you like. There's a shorthand way to add all features. So again, I am lazy, so I'm just going to copy and paste this cell. Oh no, I'm moving on a bit too quick there. But you can add in other columns if you like, but I'm not going to do that. So let's build a model where we don't just use BMI and age. We're going to put in all columns, and there's a shorthand way to do this. So we say, we'll call it Logistic 2, because I'm rubbish at naming things, is GLM, like before, so we get a bit of practice, diabetes column, Craig, actually just do it shorthand. If we put a dot, this little tilde and then a dot, it loads in all features for you. So there's a shorthand way of doing that, and data equals df, and again, the family equals binomial, i.e. logistic regression. So again, we'll just take the summary of this, Logistic 2. Okay, so now we've loaded in all of our features. And again, you get all the little m values optimized for each feature, and so on. So again, what we can read from here, we've got our p-values in this last column. And like in linear regression, remember linear regression not only was used to predict what y would be given x, but it also told you what the contribution of each independent variable is on the dependent variable. So we can see here that your glucose level, and it makes complete sense. Your glucose level is the most significant feature. It's got a very small p-value, and glucose diabetes makes sense, right? Okay, so there's two things it can do. It can predict the probability, but it also tells you as a whole which features are like most important in terms of predicting diabetes. You can read this off the p-value. So remember, a p-value, it's not in the strict sense, but a lot of people use it this way. A p-value below 0.05 means this feature is significant in its impact compared to other features. Okay, so very small value for the p-value.
You go over the start of that again.
Yeah, this here. So this is shorthand. So before, what we did when we set up our model, we said diabetes as the dependent variable, and the independent variables were BMI and age. We just fed in BMI and age, 2 columns of data, right? You could go and type out all of the features. It takes ages. There's a shorthand way of doing it. you just say diabetes is your dependent variable, and then you just put a dot, and that just means put all the features in. So it's a really lazy way of loading everything in. Okay. What's that, sorry?
So we did something like that.
Yeah, I mean, I'm sure we would have done something like this in PM272. I encourage you to be lazy. It's good in programming. Find the laziest way to do things. Okay. So again, if you wanted to, you could predict this. I'm not going to type out an X file for all different values. It'll take ages. So, but you could absolutely feed in a row of data which had all of these features in it, and you could get a prediction, and it would probably be a better prediction because you're taking into account more data. Okay, so yeah, that's how you make individual predictions, which is fine. Now that we know we can use it on one person, we want to assess the overall accuracy of our model, because at the moment, patients are walking into our clinic, we're taking note of their BMI, age, and so on, and we're just saying your probability of developing diabetes is this. Looking at our model, if you're a clinician, if you wanted to know, okay, is this model any good, or is it just randomly giving out probabilities that make no sense? I mean, the first thing you can do, what we've just done, is we've looked at the different features. The features kind of make sense, right? Glucose is heavily implicated in developing diabetes. So this is good, but you want to know the accuracy as well, because if you're going to use something like this in clinical practice, maybe to triage patients as high risk for developing diabetes, you could start them on early dietary plans and things like that. You want to know the overall accuracy, because a patient is going to ask you, okay, you've told me I'm going to develop diabetes. What's the probability that I'm going to develop diabetes? What's the overall accuracy of the model? Things like this. So this is where we need to do our test and train. So again, I'm sure you remember this from decision trees. You did a whole assignment on it last year. It was with 70% of their grade. So I'm sure you remember this whole test train scenario, right? So we're going to do this now, and it's basically the last cell in our data, in our notebook, really. Okay, so we'll create a new cell or new section. We're going to say get accuracy of model. Okay, so we're going to do a split. We're going to take 75% of the data as training and 25% as test. If you mess about with that ratio, it will give you different results. In data, you want to try and use as much of the data as you can for testing that you can get away with, right? Because the more you test on, the more measurements you take, the more robust your model is, the more confidence you have in it. Whereas if you only test on 2 people, okay, right, However, the thing is, you need a lot of that data to train a model to get a good result, to make it accurate. So there's always this trade-off of trying to get away with as much test data as you can, but also leaving enough for the training data. So, I encourage you to mess about with that ratio. You'll get to this saturation point that, you only need a certain amount of training data to optimize the accuracy. Okay, so you can definitely mess about with that, and I encourage you to do it. And people do that in the real world where they're using machine learning. But for today, we're just going to do a 75% training and 25% test split. So the way we do this, this is a piece of code that I think I gave you last year. Is a piece of code that I've used for like 10 years now, even though there are new ways to do this. But this is programming, right? If you come up with a useful function or a useful chunk of code, just keep hold of it, and you can use it for life effectively. So this is what I do. So I'm going to define this 75%. So we say floor n row df divided by 4 times by 3. Okay, so this tells us that 75% of the way into our data, if you go from row 1, you go all the way down, when you hit 576 rows, you've got through 75% of your rows in the data frame, okay? This is our bound, if you like, for want of a better name. So now we can say df. Yeah, so again, I think we went over this before. We're going to shuffle our data set as well. Always good to shuffle this when you do test stream. This could be, and it is usually the case that maybe all the people, the rows of data for people that don't have diabetes come first. If someone's ordered the table by this diabetes column, so obviously you want to mix the people with diabetes and not having diabetes. If you don't shuffle your data, you can't ensure that you're going to do that. So we always shuffle our data, it's good practice. So the way to do this is the sample. So sample is a kind of a weird name. You'd expect a function called shuffle, but what sample is, it's like take one random row. To sample one random row from the data, we're just going to sample all of the rows from the data and it shuffles it for us, okay? So sample n row df, comma. So if I just show you what that looks like. It's storing an object. So just to show you that we've not deleted or overwritten df with anything horrible. Okay, it's the same data set, but it's been shuffled. I'm going to shuffle it again because I think that's very odd. Can we do more rows? 20. Yeah, so it is shuffled. It just looks a bit suspect with the first 6 rows being 0. Okay, right. So we've shuffled our data set, which is good. I'll leave some comments in here. Shuffle 75% split. Okay, and now we're going to create our training set. df.train is df, and we're going to go from the first row all the way up to the 576 rows in this variable here. So this is 576 or 573, whatever it is. So we're going to go from row 1 all the way up to this row, i.e. 75% of the way through our training data. And when we put a comma here and nothing else after, we're saying use all, only these rows, 1 to 573, and we will leave the columns blank, i.e. just use all the columns. Okay, that's what that is. Again, what we've done here. So select random rows for all columns. So we'll do that, and then df.test is df, and then we're going to go from bound +1. So we'll continue going through the data set up to the last row. So if we do n row df, that gives us the number of rows in the data set, returns a number. So we just say go from just over 75% of the rows all the way up to the last row in the table. So that's all that does. So we got an error. Let's just have a look why. Oh, I know. Comma. Yeah. Let's just run the whole thing. I'll just do a simple test just to make sure they're all there. Head df.test. There you go. It's all fine. Okay. Right. So let's retrain our model with just the training data. Okay. So retrain model with training data. Okay, so I'll let you all just take a minute to catch up on that code cell there. Okay, so now we've set this up, we are going to now train our model on just the training data, and then we're going to run things on the test data. So I think we've got just the final 2 or 3 cells now, and then we're done for this lecture. So retrain the model. So we're going to say logistic. I'm just going to overwrite my previous model because my previous model used all the data. So I'm just going to use the training data. So we have GLM, diabet, tilde, use all columns, and then data, in this case now, df.train. And again, the family equals binomial. So that's our model. Trained very quick, did maximum likelihood estimation very quick. I think it actually tells you how many iterations it took. Yeah, so this down here, if you just scroll up to our model results, it took 5 attempts to get the best distribution. So it tried 5 different values for M and C in conjunction with each other. And after 5, it arrived at the best model. So that's what that number of Fisher iterations is. Okay, so we saved our model. I'm just going to put a mark down. So now we're going to test our model. Test model. Okay. Yeah, got a question?
Why would we need to train them?
Yeah, so before, when we initially did this, we just used all the data to train it on, which is okay because when we simulated a test scenario, someone walked in and they said, this is my age and my BMI. So when you do the prediction, you're doing it on a new person. However, we want to test how accurate that model is. And currently, when we were doing it, we could only look at how different features impacted the result. So we knew that glucose, for example, at a very low p-value, i.e. is highly implicated in developing diabetes. But what we didn't know was how accurate that model was on a sample of the population. You know, no one would trust your model. If they said to you, okay, you've got this model, the features look okay, fair enough, glucose is implicated, but anyone could tell you that. You know, how accurate is it? If I want to use this in my clinic and I send patients away and say your probability of diabetes is this, and they say, well, how accurate is that? You want to be able to say, is this accurate? So the only way we can do that is to have a big test set of people, maybe like 100 people. We train our model on some data, and then we have like 100 people walk through the door, and we compare the prediction of the model against what actually is the case. So they do have diabetes, or they're going to predict diabetes if we work backwards. And it's only from using that test set is that we can get a non-biased accuracy. Remember, you never report accuracy on the training set, okay? Never do that. We always take an independent test set. So what we had to do is we had to take our initial data set and we had to split it up into a training and a test set. And that means now we have to retrain our model just on the test, on the training set separately, and then assess the accuracy on the test set, okay? So it's like, we had to sort of change our setup in a way. We're not using all the data anymore because we know that'll give us a biased accuracy if you report on just all the data. So now we've done our test and train split, now we need to retrain. And this is how we properly assess a model.
So in essence, what you do the 75% of the training set again.
Yeah, you know, or what I would encourage you to do is, you know, get these results when you do 75% training set. I would play about with that ratio, maybe try 60%. Remember, you want to try and use as much of the data as you can for a test set without sacrificing what is a good model. You know, models need lots of data to be trained on. So there's that kind of trade-off, and you need to explore what is the right amount. So, okay, so, you know, we've trained our model. Now we need to test this. So we're going to just have a variable called logistic dot PD, stands for predictions, and it is predict. And remember, we have logistic which is our trained model, and df.test this time. So remember I did the exponent before to get the probability. There's actually there's a little shortcut in the predict function. You could just say type equals response. Response. So this will, the predict function now will automatically give you the probabilities. Okay. So we'll save that in our model. Let's have a look at it actually. Logistic.pd. Okay. So for each person in our test set, we get the probability that they're going to develop diabetes. So this is just one column of data, just in a list. And now we want to produce our confusion matrix. Okay, so we've got the predicted values, and now we need to look at if they're actually going to develop this, yes or no. Okay. Mark down. Okay, so we're going to create a table. This is just it's called a contingency table. So we're going to say when our predicted values equals yeah. So currently, what we have at the moment is we've got a column called test diabetes. Apologies for scrolling all the way up, with these values here, right? 0 and 1. Don't worry about these values. It is actually 0 and 1. So we need to say when the real value is 1, we need our predicted value to be either 1 or 0. Okay, yes, they will. Currently, though, we have probabilities. We need these basically to be either 0 or 1. And so what we can do, a simple thing is to say, if the probability is greater than 0.5, then recode that as a 1. If it's less than or equal to 0.5, we code it as a 0. So this is what we're going to do here. So as.numeric, so logistic.pd, just this object here, is greater than 0.5. So if I think I can just run that actually just to show you. There you go. Okay, so just this bit here that I'm highlighting, notice how the symbol changes. Let's get rid of that. I don't know how to get rid of that. So yeah, if you don't highlight any code, it'll just run everything. But if you just highlight this in Kaggle, it will only run what you've highlighted. It's a bit like in RStudio, okay? So that bit there, all it's doing is converting a probability to like a yes, no, 0 or 1 type thing, right? So that's good. So now we've got a decision. I'm going to compare this to the observed or the ground truth, which equals df.test, and it's just our diabetes column. So we can output this, and this is our confusion matrix. So remember, in a confusion matrix, the diagonal from left to right downwards are all the true values. So this 0, 0 is a true negative, and 1, 1 is a true positive. Remember, when we looked at our breakdown of our data, 34, the mean of this variable 0 and 1 was 34%, sorry, 0.34, which translates as 34% of our cohort had diabetes and 2/3 didn't. So we can see why this is loaded more heavily with true negatives. And then you can work out the accuracy. So I'm going to leave this as a little exercise for you in your own time. The equation for accuracy is the number of true positives, 48, plus the number of true negatives, 104, divided by all of the numbers added together in this confusion matrix. And output will pop your accuracy. I can immediately see that this is going to be a good accuracy because most of the larger numbers are on this left to right diagonal going downwards. Okay, so I'll leave that to you. And I will keep this Zoom feed going maybe for another 5 minutes, or unless, if anyone online wants to discuss anything, just give me a shout, and I can go over that. But were there any questions from this notebook today or this lecture? Got a question at the back?
You just run parts of it. Is that control and enter?
No, it's not actually. So if you just highlight, if you want to run part of what's in a cell, you just highlight it, and you notice that this has changed to this symbol here. If I just click off it, yeah. So that's all I do. I think you can probably do, can you do control enter? Will that work? No, control enter runs everything. How do I get rid of this? Oh. Oh, there we go. So I think with Kaggle notebooks as well, you can turn this notebook into a PDF, and I'll double check with the submissions team, but basically for your assignments, I think what you should be able to do is do the assignment on Kaggle if you want to, and you can export as a PDF and submit that to Blackboard. Obviously, make sure you comment things like tell me what you're doing in each section, write a little explainer. So for example, method, I am doing this because of that. You know, so you can tell me what you're doing. I think that the wisdom is, if you want to, you know, imagine you're giving your assignment or a notebook like this, just you're giving it to your parents and saying to them, understand what I've done. They need to be able to understand what you did. You need to give them as much help as possible. Show them, you know, what your motivations were when you write each piece of code. It's just good practice.
What is the assessment?
So the assessment is going to be similar to 272. Two assignments. You have a midterm and an end term. The first one is worth 30%. So again, really pay attention to the feedback of the first assessment, because if you take that on board, going into the end of term, which is worth more than double, that'll help you out. And I think, so I'm going to set the first assignment probably at the end of next week, and it will be due in 27th of November, I believe. And straight after that, you'll get the end of term, which will be due in the 4th of January. All good online? I can't see the chat, so maybe just shout if it's good.
Yeah, I'm all good.
Good. Cheers, lovely. All right. Well, thanks so much for today. Yeah. So next week it's the same time, same place. In fact, all of our lectures are usually on a Wednesday at 9, apart from week 5, which is a completely different time because timetable couldn't sort it out. So I will see you same time next week, and I'll upload a Zoom lecture link where you can log in next time. So see you soon.